lecture will continue along the lines of the first. We're going to be exploring quantum phases of matter in one of the simplest toy models of non-trivial quantum phases and transitions, which is the transistor Ising model we defined last time. So just to remind you, this is the Hamiltonian we'll be examining in detail. There are two pieces. There's a transverse field term, just a single x on every site. And there's a ferromagnetic interaction between neighboring pairs of sites. So we're interested in mapping out the phase diagram for this model. We want to see what happens as we vary the parameters j and g. So last time we began by looking at the two extreme limits of the model, right? So last time we looked at the extreme limit, say when j over g equals 0. This is the very extreme limit. And so here we saw that the ground state is quite simple. So if I draw the energy spectrum of this Hamiltonian in this extreme limit, then the ground state energy, let's say 0, the ground state just consists of the paramagnetic state. Right? So this is just the tensor product of all the states pointing along the plus x direction. Okay? So this is a trivial product state with no correlations at all. It's manifestly a trivial state. Okay? Then we looked at excitations above this state. So the first excited states have energy 2g, and these consist of spin flip excitations, right? So instead of everything pointing in plus x, you can have one spin point in the minus x direction. So this will cost an energy 2g, and we can label these spin flip excitations by a ket I. I here just denotes the position of the spin flip. And we can implement the spin flip by just applying the z operator onto this ground state. Right, so it's a z at position I will flip the qubit from plus x to minus x, right? Okay, and then one can consider even higher excited states. So for example, you can consider pairs of spin flips. Which you can label similarly by ket ij, just denoting the locations of where the two spin flips occur. And these cost twice as much energy. Okay. Okay, so now we want to kind of move away from this extreme limit and see what happens when we have some small but finite j. Okay, so we want to move along this direction. So for that, we can do perturbation theory, right? So you can convince yourself that at first order in j, or when I add a little bit of ZZ interaction, at first order in j, I won't change the ground state energy. However, I will change the wave function by a little bit, right? So just perturbation theory. Perturbation theory gives you that the perturbed state for small but finite j is the original ground state plus some mixture of these spin flip excitations, right? So there's some matrix element between ZZ. There's a matrix element for ZZ connecting the ground state and this second excited state. So perturbation theory will now mix in some of those excited states into the wave function. And this is to order j. Okay. So turning on a little bit of J doesn't change the paramagnetic state that much. It's still pretty much a trivial state with some fluctuations in the wave function, right? Okay. And now, okay, that's what happens to the ground state. What about this first? What about these first excited states? So recall that here there are L of them, right? Yeah, let me just say L states. Yeah, so there are L states, and so we're going to need to do degenerate perturbation theory to see what happens to these L degenerate states when we turn on a little bit of ZZ. Okay, and so that basically boils down to seeing how the interaction ZZ, how that couples different states in this degenerate manifold, right? So, so we want to see how this interaction acts within this manifold of L states. So you can see that if you apply Zi plus 1 to the spin flip at I, then you simply just hop it over to the next side, right? So Zi will cancel out Zi in the I state, then Zi plus 1 will produce the spin flip at I plus 1. Okay. So ZZ just hops an excitation from I to I plus 1. And similarly, Zi minus 1, Zi, acting on I, hops it the other way. Okay? So now this perturbation, J sum over ZZ, just serves as an effective Hamiltonian in this manifold of L states. So basically, the matrix elements of this effective Hamiltonian are just given by minus J, and then it either hops to the right or it hops to the left. Okay. Okay, so this is a simple hopping Hamiltonian in this set of L states. So can anyone tell me how we can diagonalize this effective Hamiltonian? Like, how can we construct eigenstates for this Hamiltonian? Sorry, yeah, that's the right direction. So we're going to need to start superposing these localized basis states. Yeah, it's the right direction. So recall that this Hamiltonian has two symmetries, right? This Ising symmetry, the spin flip symmetry, and also translation symmetry, right? So so as usual, symmetry is helpful in pointing you toward the right basis, and to take advantage of translation symmetry, we want to work in the eigenbasis of translation, right? So we want to work in the momentum space. We want to work in plane wave states, right? And indeed, that's how we can easily diagonalize this effective Hamiltonian. So we can define a momentum state, K, with momentum K, to consist of some superposition of all the localized states with some phase factor e to the I kj. Okay? And so now you can see that it's pretty straightforward to check that H effective, this effective hopping Hamiltonian, is diagonal in this momentum basis, right? So you can check that H effective acting on such a momentum state just pulls out a number. And this number is just coming from here. It's minus J. And then you get a phase factor for hopping right, e to the ik, or from hopping left. Okay, and this is just minus tj cosine k. Okay, so we see that the effect of this ferromagnetic coupling is to hop these spin flip excitations, and so now these spin flip excitations can lower their energy by hopping. Okay, so you can see that, for example, for the k equals 0 mode, the k equals 0 mode reduces its energy by 2j due to the fact of this hopping interaction. Okay, so now the k equals 0 mode actually has energy 2g minus 2j. Okay. So all this is just to see what happens to this set of first excited states. You can see that the hopping turned the fully degenerate set of L states into an energy band. Right? So now I can label these states by their momentum k, and they have a given energy given by this. Okay. So the whole point of this was just to show that when we turn on finite j, some of these states come down in energy, okay, as we turn on finite j. Any questions about that? Yeah, sorry. Okay. Okay, so that's the single spin flip. What about the pair of spin flip excitations? So that's a little bit trickier, and so we won't go into detail about what exactly happens to those. Let me just present, not a very rigorous, but sufficient picture that allows us to understand what happens to the energy of this second excited states. And so now we have pairs of these spin flip excitations, right? And when we have two of them, now the momentum of these spin flip excitations no longer fully determines the energy, right? So here you have one excitation, each momentum has a given energy, right? But now when we have two spin flips, right? We have a total energy E, or let's say total momentum K, that's given by the sum of the two individual spin flip momenta. And there are different ways to decompose the total momentum into K1 and K2, right? This is degree of freedom now. And so there'll be different possible total energies as a result. Okay. So you can check that now instead of like a band of excitations, one actually has a continuum of excitations. Okay, so one actually has a continuum of excitations. Due to this degree of freedom, different ways of decomposing momenta. Okay? But the important thing, again, is just that the effect of finite j allows one to lower the second excited state energy as well. Okay? So as a simple exercise, you can check that one gets this two-particle continuum for this manifold of two spin flip excitations. Again, it's not completely rigorous because these spin flip excitations are not independent. They actually interact with each other. So the long story is more subtle. But for our purposes, I just want to show that the energy here comes down as well. Okay. Okay, so that's what happens on the paramagnetic side. Basically, we see that the excitation energies come down, but nothing really drastic changes to the ground state. It was trivial and it's still trivial. Okay, so in that sense, it's kind of stable to adding finite j. Okay. Okay, so let's now see what happens on the large j side. So here, we can again draw an energy spectrum, right? So I've so last time we showed that the ground states can be thought of as either the GHZ plus or minus states, or as the product states 0, 1. Okay. And we also discussed that there are the first excited states occur at energy 4J, and these are domains or pairs of domain wall excitations, right? So these are things like 0, 0, like 1, 1, 1, 0, 0. Right, so you have like a domain of the incorrect spin in a sea of the other one. Okay, so this is what happens for j over g equals 0. And now we want to see what happens when we turn on finite g. Okay. So first, now we even have to work a little bit for the ground state, right? The ground state itself is twofold degenerate, and we should first ask what happens when we turn on finite g. Okay. So you can see that to do something non-trivial, the perturbation x, sum over x, has to couple the two degenerate states, right? But in order to couple them, it has to go to very high order in perturbation theory. You need to go to order L to flip all the spins to get the other state, right? So it's basically the effect of finite g is to produce some exponential splitting in these two degenerate states. So you have some very small splitting that's exponentially small in system size. Okay. But a constant multiplying L. Yeah, that's true. Actually, no. Why do I need that? Yeah. Like ultimately, the exponential factor is coming from a g over j to the L power, right? Yeah. Okay, so so the ground state gets split by a little bit, and now we want to see what happens to these domain wall excitations, right? So this is the domain wall is already a little bit more complicated than the paramagnetic side, and so we want to basically use a trick to understand these excitations better by using a duality mapping. Okay, so this is also a good excuse to at least introduce one simple example of the duality. So we'll want to basically map this large j side to the large g side, which we already analyzed in some detail. Okay, so now let me introduce this duality which does the job. So duality is a very powerful concept in physics. It basically allows us to map hard things on one side to easier things on the other side. So it's a very powerful technique. And so in this case, we're gonna map the large J side to large G side and vice versa. So how does this work? So let's first define a new set of variables for these spins, okay? So before we had a 1D system, right? And we had our spins living on a lattice, labeled by I plus 1, etc. And now we're going to want to define another set of spins living in between, okay? So we're going to define another set of spins living in between. So at sites I minus 1/2, I plus 1/2, etc. Okay. And so we're going to label these new spins on the in-between sites by a tau variable, okay? So we're going to say that tau at I plus 1/2 corresponding, we're going to identify tau x for the I plus 1/2 location to just be whether or not there's a domain wall between the physical spins, okay? So we're going to define tau x this way. So basically, tau x equals plus or minus 1 denotes whether there is or is not a domain wall, right? So ZZ being 1 or minus 1. Okay, so what about tau z at I plus 1/2? Well, this is basically a domain wall creation operator, right? It flips between +1, -1. But remember that to create a domain wall, to create a single domain wall, this has to be a non-local operator in the original spin language, right? To create a domain wall, you need to flip all the spins to the left, for example, right? So tau z would correspond to something like a product of the original spin x operator for all sites to the left of I. Okay, so this is a non-local operator in terms of the original qubits. And this is another common property of dualities. What's local in one language is often non-local in another, and vice versa. Okay. Okay, so we've mapped ZZ to this tau x variable, and now we can see what the other term in our Hamiltonian corresponds to, right? So we can look at just spin flip for qubits. So if I flip a qubit at I, then I basically create two domain walls at I minus 1/2 and I plus 1/2, right? When I flip a qubit, I flip the domain walls on either side as well. So xi will correspond to two domain wall creations, so tau z at I minus 1/2, tau z I plus 1/2. Okay? Yeah. Oh, sorry, yeah, DW is domain wall. Yeah, right. Okay, so now I've used like a different set of variables to, that's suited just to look at location of domain walls, and now I can just plug in what happens to ZZ and X in my original Hamiltonian, and I see that the resulting Hamiltonian in terms of tau variables is H prime equals minus J sum over tau Z, sorry, yeah, tau X I minus J sum over tau Z I minus 1/2, tau Z I plus 1/2. Okay? Okay, so you can see that the roles of J and G have flipped here, right? So J used to be the coefficient for the ferromagnetic exchange, then now it's the coefficient for the X field in this tau variable. And similarly, G used to be the coefficient of the field, and now it's the coefficient of the exchange in the ferromagnetic interaction for tau Z. Okay? However, there are some subtleties now. So I've swept a couple of things under the rug here that are quite important. So one subtlety is that these tau variables are not all independent, right? Can anyone tell me why they're not independent? Yeah. Oh, sorry, this is X. Yeah, sorry, my handwriting is pretty messy. Yeah. Subscript I, this is I. Oh, yeah, that's right. Okay, I guess strictly speaking, yeah, it's over I plus half, yeah. Or over I, and then I plus half, yeah. Summing over all the sides of tau, yeah. Yeah, so why are the tau variables not all independent? The tau here. Sorry, what was that? One flip of tau will influence others, or? So remember how tau x is defined. It's a domain wall variable. So it's like ZZ, right? Are ZZs all independent or not? Why not? Okay, so maybe I should remind you that just for concreteness, I'm considering a system with periodic boundary conditions. Okay, maybe I should have said that, reminded that from last time. But so we're having a ring of these, and ZZ acts on all nearest neighbors, right? So you can see that if you take the product of all tau x, right? If you take the product of all tau x, that's the product of all these pairwise ZZs, and the Z's all cancel in pairs, right? So this is actually the identity. Okay. Or the more physical way of saying this is that tau x is a domain wall. It tells you if there's a domain wall or not. And remember that domain walls are always come in pairs, at least on a system with periodic boundary conditions, right? So there's this parity constraint on the number of domain walls. The product of all of them have to be 1. Okay? So this is very important constraint that one has to keep in mind when dealing with this Hamiltonian H prime, right? So it's defined in tau variables, but these taus are subject to a constraint, okay? The other way of saying this is that the map from physical qubits to these domain wall qubits is not a one-to-one map, right? Because when I specify domain walls, there's still, like domain walls only specify a physical configuration when I've specified a reference spin, right? When I tell you how things are all related to each other, I need to specify a reference. Then I can determine the physical configuration, right? So there's the map from physical qubits to domain wall qubits is actually a 2-to-1 map, okay? Okay, so in what sense is in what sense are H and H prime related? So I've just told you that the Hilbert space doesn't even match up completely, right? It's like a 2-to-1 map, right? And so that's because I swept another thing under the rug here, and that is when I define this relation between x and tau z, there was also a degree of freedom here a choice that I made. Okay, so you can actually, define some. You can define some. You have a choice of defining just a coefficient here, right? So basically here, I've made a choice such that the product of all the tau z's, is also 1, right? This is also the identity for exactly the same reason as we just argued here, because all the z's cancel in pairs. But the product of tau z's is just the product of x's for the physical qubits. Okay? So I've implicitly made a choice here that fixes the symmetry sector of the original qubits. Okay, so by making this particular choice here, I've assumed that the original Hamiltonian was in the spins of the original Hamiltonian are in Ising parity even sector, basically the product of x equals 1. Okay, so the long story short, H, the Hamiltonian H there, with this constraint here, has the exact same spectrum as H prime here in the tau variables with this constraint. Okay, that's the upshot of this change of variables. Okay, let me pause there for questions because with dualities you can get pretty confused easily. Yeah. Oh, this is just an index. You can use your favorite numbering. It's just a notation for the location. Yeah. We're kind of imagining there's a fictitious qubit here. It's like it's just a different description of the system. You can think of it as like a virtual qubit, just a different way of writing the Hilbert space, writing the Hamiltonian. Yeah. It's just a change of variables. You don't have to think of it as a physical thing, right? Yeah. Yeah. This is just to facilitate our analysis of the original Hamiltonian. Yeah. Yeah. Wait, so sorry, which variable are you talking about? The taus or the original qubits? The original qubits, okay, you have z and x, yeah. Yeah, the X one flips a qubit, flips a physical qubit, and so what does that do to the domain wall right next to it? Like, it creates two, right? Yeah, yeah. It creates or annihilates, depending. Yeah. So, what is doing Z in the original qubit? Ah, okay, okay. Yeah. Uh, that's a good question. Right. Yeah. So Z breaks the Ising symmetry, right? So Z anti-commutes with the product of X symmetry, right? Um, let's see. And I think we're only here mapping things that preserve the Ising symmetry. Let's see. Well, okay. Okay, no. Yeah, sorry. Yeah, so again, we really worked out what tau Z is in the original qubits, and these two sides are dual to each other, right? So tau Z, I argued, is a domain wall creation, right, which involves flipping a whole string of qubits before it, right? So similarly, uh, if I wanted to do the physical Z operator, that would correspond to a string of tau x's um, behind it. Okay. Although there is an issue with the boundary condition here, I think. Yeah, let me think carefully about this. It's a pretty subtle question. Let me think carefully. Yeah, it's a good question. Good question. Okay, so yeah, so basically this duality interchanges large A and large G, and indeed you can check that the paramagnetic state gets mapped to the GHZ state in the other language, right? So, for example, GHZ state basically is when everything is aligned, so there's no domain wall, which means that all the tau x's are pointing the +1 direction. So the GHZ state, when there's no domain wall, is a paramagnetic state in the tau language, and vice versa. Okay, yeah. Um, yeah. So I think uh, I think this is related to the other question about whether or not um, yeah. It's true that this string maybe needs like an endpoint to be well defined. Let me get back to this question about how Z in one convention is written in terms of the other. Yeah, I don't want to say something wrong right now. Yeah. Yeah, good questions. Very good. Yeah. Well, it's not between Z and X. It's like ZZ and X, right? Right, this is the identification, right? Yeah. Oh yeah, yeah, like yeah. This is just this is just a trick to help analyze the Hamiltonian. Okay, well, it's more than a trick. There's some, um, I think nice physics behind understanding the critical point for this model as well. But for now, just view it as a trick for understanding the ferromagnetic phase. Yeah. Okay. Yeah. Yes. Yeah. So tau z is creating a domain wall, right? Um, yeah. So okay. So I think when you have periodic boundary conditions, tau z just has no translation in terms of the physical spins, right? Because with periodic boundary condition, again, you need to create a pair of domain walls, right? Yeah, so yeah, sorry. Yeah, I don't know why I was so confused earlier. So with periodic boundary conditions, tau z has no. Yeah, okay. So this really I think should assume open boundary conditions here. This statement here. Okay, so yeah, I want to consider periodic boundary conditions. This statement here assumes open boundary conditions. Okay, so with periodic boundary conditions, it's not possible to create a single domain wall by itself. So there's no translation like this possible. So similarly, with periodic boundary conditions, there's no translation of a z operator into domain walls either. Okay. With open boundary conditions, you can though, because now you can actually create a single domain wall, right? By flipping a bunch of spins up to an endpoint, right? Yeah, thanks for the questions. Yeah. We want to consider periodic boundary conditions always. Let's say we stick with that throughout. This comment here was for the case of open boundary condition. Well, like what would happen there, right? Yeah, yeah. Most of this will just be about periodic boundary condition. Very good. Yeah. Can you speak louder? Sorry. Yeah, I'm just defining tau in this way. Like tau x is this, right? It's just yeah, like basically a definition of the algebra of tau, right? Okay. Let's see. Where was I? Okay, so now that we've mapped the two sides, now we can see what happens to these domain wall excitations here, because we already figured out what happens to all the spin excitations on the paramagnetic side, right? And we just said that the spectrum of H in a given Ising sector is the same as the spectrum of H prime given the constraint, given this constraint, right? So So basically, I can look at domain wall excitations in this given Ising sector, and that maps to some spin flip excitations on this side. But recall that I have this constraint that product of tau x is 1, right? And so a single spin flip excitation of tau would violate this constraint, right? So basically, the domain wall excitations on the left side map to pairs of spin flip excitations in the tau language, right? The physical way of just seeing that is just that, you know, the domain walls are, yeah, I'm looking at a pair of domain wall excitations, so that should map to a pair of spin flip excitations, right? So we saw that here, the energy of these two particle excitations comes down, and so indeed, that's what should happen here as well. Okay. And let me just comment that one can also do perturbation theory on the GHZ states or the 0-1 states, very similar to what we did to the paramagnetic state here. And you can see that you just mix in some domain wall excitations, but you don't qualitatively change the long-range correlations of the ferromagnetic states here. Okay, so you just mix in some quantum fluctuations when you turn on G. Okay, so the upshot here is just that we have two extremes. Now we're trying to come toward each other, but the long-range correlations for these two extremes don't change very much as you turn on coupling in the other direction. Okay, and similarly, the energy gaps they close a little bit, but that's about it. Okay. However, what this duality suggests is that something drastic will happen when J equals G, right? When J equals G, then you have a self-duality, right? ZZX goes to X, ZZ. And that suggests that something drastic will happen right in the middle where J equals G. Okay. So indeed, if we extrapolate, you know, we might see these excitations come down all the way down here. These come down all the way here. And the energy gap might close right at J equals J. Okay. So there is something drastic will happen. And so we suspect that there will be a phase transition here where the ferromagnetic order gets destroyed by all these domain wall fluctuations coming down to ruin the ferromagnetic order. And here, these spin flip excitations also come down and destroy the paramagnetic order in some sense. Okay. So this is what the duality suggests. But it turns out that we can actually solve this model completely using a different transformation. Okay. So I don't know if I have time to, yeah. It becomes symmetric with a constraint, that's right, yeah.
So the fact that you are joining, the yellow lines are projected out because of the bottom.
Yes, that's right, yeah.
Then I'm a bit confused why you are drawing some lines coming from the yellow. The yellow are projected out.
Well, they're projected out only if one wants a self-dual Hamiltonian, right? The physical Hamiltonian with both Ising even and Ising odd sectors, they're still there for the physical Hamiltonian, yeah. But yeah, the duality would get rid of the yellow, right? Yeah, so maybe I can just begin. Let's see. Yeah, I can. Yeah, let me just begin a different type of duality that actually can solve the model explicitly. And this is basically a what's called a Jordan-Wigner transformation. Or boson to fermion transformation. And yeah, let me try to motivate why we want to change to the set of variables that we will change to now. So again, to solve the model completely, we want to be able to describe both types of excitations, right? We want to describe excitations on the ferromagnetic side and on the paramagnetic side. So again, these are domain wall excitations, and these are spin flip excitations. So to solve the model completely, we want to describe both at the same time, and so that motivates one to consider a composite variable that's a combination of spin flip and domain wall creation. Right? So basically this composite involves both a domain wall creation bound to a spin flip, which is Zi, right? And so if you yeah, so if you translate into the original physical qubit language, then you get some string of X operators. Multiplied by Zi. Okay. So all this just motivates one to consider these type of variables, which are strings in the original qubit language, but let's look at their statistics with each other. Okay. Yeah. Okay. So actually, I think this will be a longer story than I thought. Maybe it's more constructive to just present a simple exercise related to some of these wave functions and efficient representations of them. Yeah, let me continue this Jordan-Wigner next time. Sorry, and let me just present an exercise based on some things we discussed today. Okay. So yeah, let's see. Yeah, so recall that when we perturbed by adding a little bit of J here, this product state wave function got a bit of quantum fluctuations, right? So it got some linear combination of two spin flip excitations. Plus higher order, right? So we went from a product state to a perturbed wave function with just a little bit of quantum fluctuations, a little bit of entanglement, right? And so sometimes it's useful to represent these wave functions with a little bit of entanglement in a very efficient form. Okay, so there's something called a matrix product state. Yeah, there's something called a matrix product state, which is very efficient at capturing low entangled wave functions. Okay. So yeah, so you can define a wave function in terms of some spin configuration as a trace of a product of a bunch of matrices. So MS1 all the way to MSN. Okay, so here, here M is some D by D matrix, where D can be some parameter that you can choose. For our purposes, let's just choose 2 by 2. That'll be sufficient for this exercise. So M is a 2 by 2 matrix, which also depends on the value of S1, right? So S1 to Sn are computational basis states. They're strings of zeros and ones. It's just how you specify the wave function. And so M0 will be some 2 by 2 matrix. M1 will be some 2 by 2 matrix. And this is a way to parameterize this many-body wave function. Okay, I'm just defining a certain ansatz for this wave function. Okay, so again the power of using these so-called matrix product states is that one can now capture wave functions beyond simple product states, right? So as you can see, if you diagrammatically draw this wave function, then each matrix M has some index corresponding to the physical spin, and it also has two indices corresponding to the two indices of the matrix, right? And so now by doing a matrix product and then tracing over it, that just corresponds to stitching these matrices together. And then trace will identify the two ends. And so you have a nice pictorial representation of this wave function that clearly can have some entanglement now, right? It's not a simple decoupled product state. Okay, so the exercise is just to learn about the basics of this matrix product state, and as an exercise you can try to represent this wave function as a matrix product state with simple 2 by 2 matrices for M0 and M1. Okay. Yeah. And again, if you have any questions about that, feel free to let me know. Okay. So that concludes this lecture. Next time we'll talk about the Jordan-Wigner transformation, and then we'll wrap up the transverse Liesing model. And also just try to see what the implications are for what we've learned from this example for phase of matter. Like what general principles have we learned from it? Okay. I'll take some questions.
Questions? Everybody's happy?
Mm-hmm.
A comment on the first exercise.
You mean the one from last
Yeah,
time?
from last class.
Yeah. Sorry, I didn't say that much. Yeah, the exercise last time was just to implement a simple code that diagonalizes this Hamiltonian, say for a choice of parameters like j equals g equals 1, just to diagonalize it on the computer using both exact representation of the Hamiltonian as a big matrix or as a sparse representation of the matrix, but then using a sparse algorithm to find the low-lying states. Okay, so just numerically compute the low-lying eigenvalues and eigenvectors of the Hamiltonian. Yeah.
And to get the correct answer of all plus.
Yeah, yeah. You can test that. You know what I'm saying is correct, right? It would be a fun numerical exercise as well to check all these statements, right? Does this spin excitation really come down? Like, is there a band of excitations? Is there a continuum of excitations here, right?
Okay.
You can check as much as you want numerically too. Yeah.
Thank you.
I would like to know if you can give me more reference, like a book, or because this is for me a new topic. So
This or
yes, old.
oh, you mean like all of this?
Yes.
Uh, yes, I think well, Subir Sachdev is like a quantum phase transitions book that's I think quite good.
Can you write the name, please?
Yeah, it's Sachdev quantum phase transitions. Yeah, also yeah, I'll try to think of some more that I think would be useful. Yeah.
Thank you.
Other questions?
I want to know if you can repeat why is the lack of the symmetry in this graphic?
Yeah, that's right. So remember that I erased part of it, but the duality involves these two Hamiltonians in two different variables only when there's a constraint on each side. So the constraint on the physical qubits is that product of x is 1, okay? And the constraint here is that the product of tau x is 1. So the duality only applies when enforcing a constraint on both sides. Yeah. So okay, so actually this brings up another I think useful exercise. So here I formulate the duality when the original Hamiltonian is in the Ising even sector, product of x is 1 sector. But let's say you want to make a duality for the product of x equals -1, the odd even sector. How do you need to change the h prime to make that into a duality? So that's another good exercise to understand this better. Yeah.
Okay, thanks.
More questions? Okay, so let's thank Tim again. So before you go to lunch, we'll take a picture now. So just if you can come down.